Okay, so we are doing the second law of thermodynamics. Okay. You saw that the first law of thermodynamics was a conservation of energy principle. Okay. So you needed the second law of thermodynamics because these laws were not enough to explain certain things. Okay. So for instance, we saw that if you have a hot cup of water in a room, okay. Okay. This process occurs in nature, okay, and this does not occur in nature. Okay. So in the top process, heat flows from here to there. Okay. And to go from here to there, heat would have to flow from there to here. Okay. See, this process and this process, energy hasn't been created or destroyed. The first law allows that. Is cool with it. The first law is cool with this process and that process. But you never observed this in nature. So that's why you needed the second law. Okay? So the second law says this is not possible. Okay? And so that's why you need it. All right, we learned that why this process doesn't happen. Okay. Why doesn't this process happen? We talked about something called microstates. Okay. And I will just give you the simple form of that. Okay. So this state, let's say, has a 10 to the power of 24 microstates. I'm just making up a number. That's a trillion microstates. And this state has 10 to the 6 microstates. Okay. And the punchline is, in each microstate, the system spends 1 second, equal time. All right. So the system, you won't find the system for a very short time, and you'll find the system in this state most of the time. Okay, so the probability of being in this state is much higher than in being this state. So that's all you see. Okay, so even if you start off with this state, there are so many more microstates that the system will tend towards that. Okay, so here's another very good example that you intuitively know. So here's this room. Right now the air is spread evenly in this room. Okay. Is it possible that all the air will get in on that side of the room? Yes, it's possible. The number of microstates is very small. The number of microstates is very large. So the system mostly spends all its time here. It might spend 1 second, and I'll give you numbers for this, in a trillion years. Okay, and so that's why you're never worried about all the air getting in there. Okay, so it's all a probability game. Okay, the chance of it happening are there, but they're just so small that you probably will never encounter. Well, you'll definitely never encounter in your life. That's the idea. Okay, did you guys understand that? Okay. All right, so so we learned that entropy, so in this process, so let me clean up the diagram. Okay, so going back to that example, here's the water at 100 degrees Celsius, room at 20 degrees Celsius, and this system this system will evolve toward that. This never happens. Why doesn't this happen? The second law introduced a quantity called entropy, and entropy increases in this direction, and entropy would decrease in this direction. And nature doesn't allow any processes where entropy decreases to happen. Yeah? All right. So entropy is log W. If you want, that's the formula for entropy, where W is the number of microstates. And that's very hard to calculate, so in practice we'll never calculate that. Okay, so W is very hard to calculate for systems. Okay. All right.
What is the K in that equation again?
And Boltzmann's constant. Yeah, and that was the formula Mr. Boltzmann came up with.
Gotcha.
Remember, Mr. Boltzmann was a pretty smart dude. Yeah? So entropy is a measure of disorder in the system. It's a state function, and entropy always increases in all natural processes. Okay, we saw that this is the second law of thermodynamics. Entropy, okay, for an isolated system, entropy always increases. Change in entropy is greater than 0 or equal to 0. When is this 0? Anybody remember? For reversible processes. Okay? Reversible processes are ideal processes, and in all natural processes, entropy increases. Mm-hmm. Okay. So in all the processes we see for an isolated system, entropy always increases. Okay. So we saw all of that. Okay. So a practical way to calculate entropy. Now, what we said was this is hard to calculate. Okay. So this actually calculates the entropy for a given state, but this is hard to calculate because this is hard to calculate. So what do you do in practice? In practice, what you do is when a system goes from an initial to a final state, you can calculate the change in entropy. And the change in entropy is calculated like this. The change in entropy is the sum of infinitesimal changes, okay, for little steps. And what is that infinitesimal change? How much heat did you absorb at what temperature? And so you add all those numbers up and you get the change in entropy. Okay? And this is what's calculated in practice. Okay? Do you guys understand that? Okay. Okay, so this is what's calculated in going from the initial state to the final state. All right, so we gave you this formula for if you're dealing with the ideal gas, and if its temperature changes from, so when it goes from a initial to a final state, and its temperature has changed by this much and volume changed by this much, there's the change in entropy. Okay?
We would use that when we have
An ideal gas, yep.
ideal,
Okay, and if you wanted to know the change in entropy, yep. All right. So we saw all of that. For reversible processes, change in entropy is 0. For irreversible processes, change in entropy is greater than 0. And then we learned about heat engines. What do heat engines do? They use heat and convert some of that to mechanical work. Okay? So they get heat from a source, convert some of that to work, and throw away the unconvertible, the part that cannot be converted remains as heat, which you dump in a reservoir. Okay? Ideally, you would like to convert 100% of that heat to work, but of course that's not possible. That's not possible, and that's what the second law says. Okay? All right, so for a heat engine, we are interested in the efficiency of a heat engine. If you absorb this much heat, okay, how much of it got converted to work and the rest got dumped. Okay, so this is the efficiency of a heat engine. And you saw that in practice, heat engines are, your car is a heat engine, which is about 20% efficient, 20 to 25. The best thermal power plants are coal power plants, which are about 40%, 35 to 40% efficient. Yeah, nuclear power plants are also about that efficient.
The QH, that stands for changing heat.
Now that's the heat absorbed from the hot reservoir. Okay. So that's the heat released when you burn gasoline, for instance, in your car.
Okay.
Okay. Okay. So we use quite a bit, we use a lot of heat engines in our life. In fact, okay, so currently the world's 80% of the world's energy is coming from fossil fuels. Okay, and what do you do with fossil fuels? You burn them. Okay, and so you're using them in heat engines. Okay? So 80% of your, and about 65% of this gets thrown out as QC. 65% of 80% is about half of your energy gets thrown out the window. Okay. All right. So you want to maximize this efficiency, okay? And Mr. Carnot gave an upper limit for the efficiency of a heat engine. Okay? And what Mr. Carnot found was the efficiency of a Carnot engine, just depends on the operating temperature. Okay? And all real heat engines operating between these temperatures have less efficiency. So this is the upper limit. And these temperatures are in what units? Kelvin. Okay. So again, heat efficiency is W by QH. Okay. So you want efficiency to be 1. You would, okay. How can this efficiency be 1 if this is 0? Okay, so if your sink temperature is 0 degree Kelvin, and that's not possible, or if the temperature inside your cylinders is infinite, that's also not practical. Yeah. So for those cases, you could have an efficiency of 1. And then we learned about refrigerators. Okay. And the way, so what do refrigerators do? See, here's a colder temperature, and here's a hotter temperature. They're removing heat from a colder temperature and dumping it in a hotter temperature. That's what they're doing. Nature won't do that. So that's what a refrigerator does. It removes heat from a colder region and dumps it in a hotter region. It's making water flow uphill. How do you do that? You have to do work. You use a pump to do that. Okay? So it's making heat flow uphill. Well, how does it do that? So a refrigerator uses the following idea. When you go from a liquid to a gas, you need heat. You have to absorb heat. And when you go from gas to liquid, you have to dump heat. Right? All right, so let's see how this happens. So here's a refrigerator. Inside the refrigerator, you have an evaporator. You have a coolant flowing. Okay. In the evaporator, what do? You go from liquid to gas. And so you're absorbing heat. So you absorb heat at a region of lower temperature. And then you're going to come on outside. This is in the kitchen. And you're going to here's high pressure vapor, this is vapor gas, and you're going to convert it into liquid. Outside, you're going to go from gas to liquid, and you're dumping the heat out here. Okay.
Is it 65 calories or how much was it?
For water, the latent heat for water was 540 calories per gram. But you're not using water here as the liquid, okay?
So that's the, how much calories you removing? Is it 540?
No, I mean, if your coolant was water, you would remove that much, but your coolant is not. Okay, so how do you decide what your coolant is going to be? What is the liquid you're going to use? Okay, so inside the refrigerator, if you want to maintain 0 degrees Celsius, you want the coolant's boiling point to be below 0 degrees Celsius. Okay? So that's what decides what coolant you use. Okay. Anyway, the idea is when in the evaporator, the coolant turns from liquid to gas and it absorbs heat. And then when you come outside, you turn that gas to liquid and it gives up heat. So you're absorbing heat there inside the refrigerator and dumping it in the kitchen. Okay. So that's the process. The coefficient of performance, okay? How good is your refrigerator is your question. Okay? So the thing is, how much heat did you remove from inside the refrigerator? That's the amount of heat removed from inside the refrigerator, which is your goal. And how much work did you have to do for that? Okay. So the refrigerator sitting in your kitchen has a COP of about 5. What that means is for removing 5 calories of heat, you had to do 1 calorie of work. Okay. So your water heater, your air conditioner, and your refrigerators are 3 of your biggest energy hogs in your house. Okay. All right, now I'm going to quickly go over the rest of the slides. I won't go into the details. You guys can read it, okay? So remember, entropy measures disorder, and we introduced this formula. What is K, my friend? Very good. Log W, what is W in there?
The amount of microstates.
The number of microstates, okay? So for a given macrostate, so for instance, the gas in this room, what is the macrostate? Its pressure is 1 atmosphere, its temperature is 20 degrees Celsius, its volume is about 1,000 meter cube, okay? So those parameters tell you what is the state. For this state, how many microstates are there is the question. Now that's a very hard calculation, and the number of microstates will be very, very large, okay? All right, I'm just going to specify the microstate of a system, we must specify the state of each individual particle. Where is the individual particle? How many? There are 10 to the power of 28 particles. Where are the particles? How fast are they traveling? And all that kind of stuff. Okay? All microstates are equally probable. Okay, so that's crucial. Again, you'll need this at a higher level. Okay, a macrostate is a description of a system in terms of macroscopic variables like what is the pressure, temperature, and all that kind of stuff. Okay. For a given macrostate, a number of microstates are possible. Okay. The number of microstates corresponding to a given macrostate is called the multiplicity of that macrostate. Okay? So the multiplicity, so for example, this macrostate, the gas in this room, again, I'm just guessing. It probably has 10 to the power of 100 microstates. Okay? I just made up that number. Do you guys know what this number is? It's got a name.
Google?
Google. Okay, so they were very modest when they were naming themselves. Do you know what the rationale is behind that name? Okay, so they're saying even if there were this many pages in the world on the internet, they're going to show them to you. There aren't that many, not even close again, but this is the number of protons in the universe. Okay, so Google is bigger than that. Okay. All right, so I'm going to show you some numbers. Okay, again, anybody remember how many particles are there in this room? Very good, 10 to the power of 28. Okay. So the number of microstates for that many particles will be very, very large. Okay. So what we're going to do is we're doing a calculation for a very simple problem. Okay, so let's say these are gas particles. What is the probability of a particle being here? It's 1/2. That's half the room. Okay. So let's say we have 100 particles. Okay. And what is the probability of all the particles being in this half of the room? It's 1/2 to the power 100. Okay. So, so for the particles to be evenly spread, if that's close to 1, the probability of all the particles being in this half of the room is that much. Okay. So what we are saying is, if all the particles are evenly spread and they spend 1 second there, all the particles in this half of the room will spend that much time, that many seconds. That's what that means. Did you guys understand that? Or if the particles are evenly spread, okay, so this is what it translates to. If the system spends 1 second per microstate, this would take about 10 to the power 22 years. Okay. So I'll draw it. So what that statement is saying is the particles spread all evenly for 10 to the power of 22 years spent here, the particle will spend 1 second there. The system will spend 1 second there. So that's how many more microstates there are for this configuration than for this configuration. That's the statement. All right. Well, what is this? Do you guys know the age of the universe?
7 billion years?
I'm sorry?
7 billion?
It's 13.8 billion years. So we'll say 10 to the power 10 years. That's 1 trillion times the age of the universe. Okay, so if 1 trillion times the age of the universe is spent here, and just for 100 molecules, you'd spend 1 second there. So it's not, I mean, it's not impossible, but it's very, very, very unlikely. And that's why for this many number of particles, you don't even have to worry about all the particles being on this side of the room. You know? And you knew that intuitively. Yeah. All right, so we can thus conclude that the second law of thermodynamics is never violated in any practical situation. Okay. Okay, so this graph shows you, so this is the number of microstates you have for evenly distributed particles. You want this, the number of microstates is almost 0. So the probability is essentially of 0 of being in that configuration. That's what this graph is telling you. Okay. All right, so the slides go through the derivation of the Boltzmann's law, okay, briefly. And like I said, Mr. Boltzmann, an Einstein caliber scientist, was most proud of that formula. Okay. Again, the Boltzmann's constant, and that's the number of microstates for a given macrostate. So for instance, if you can calculate the number of microstates for a black hole, you can be friends with Mr. Stephen Hawking. Okay. He did calculate it. No. All right. Do you guys own a heat engine?
Do we want to do
Mm-hmm.
our vehicles?
Yep, your cars are heat engines. Okay, so let's see how they work. Okay. What happened? Okay, there you go. All right, so what does a car engine do? It gets heat from burning gasoline and then converts that to work. Okay.
I'm Jake O'Neill, creator of Animagraphs, and this is how a car engine works. Let's start at a single piston, the powerhouse of the engine, and work our way outwards. The four-stroke cycle. When a piston travels to the end of its range, whether up or down, that's a stroke. Car engines use a four-stroke cycle, and it goes like this. First, intake. The piston descends, sucking an air-fuel mixture into the cylinder through the intake port, with both intake valves open.
Okay, so now you've taken an air-fuel mixture, okay, and you're going to burn this fuel. The air is needed to, when you burn, you're combining it with oxygen. That's when heat will be released.
The intake port, with both intake valves open. Next, compression. With all valves closed, the piston comes back up, compressing the fuel and air mixture for more powerful combustion.
Okay, so you've compressed it, and now you're going to light it. Okay. Now the deal is, when you light it, what is it that you want? You want all the fuel to burn. Okay, you don't want any fuel to remain, so you don't want to waste energy. Okay. Now, to make sure that all the fuel burns, the greater compression you have, the warmer it is, it's ready to explode, and you just light it up. Okay? All right.
Then, the power stroke. An electrical spark ignites the compressed fuel and air mixture, and the resulting combustion forces the piston to the bottom of the cylinder again. It connects.
So that expanding gas, now it's doing work. So the heat released is doing work now. So that's the punchline. Okay. So when the gas expands gas, it's pushing on the piston, and you use connectors to turn the wheels on the car. Okay. So now all your work is done. So once the work is done, what do you have to do? Now you have to empty these burned gases and recharge. Okay? So that's what will happen.
Rod transfers this power to the crankshaft. Finally, exhaust. The piston comes back up, pushing the spent mixture out through open exhaust valves and the exhaust port. connecting multiple pistons. For smooth power delivery, pistons take turns firing. The firing order for this engine is
Okay. Did you guys understand that? Do you want to see that first part again? Are you good? All right. Well, it's linked there, so you can go see it again. You know? Okay, so you saw that a Carnot engine was an idealized engine, okay? And what the usefulness of it was, what was the usefulness of the Carnot engine, even though it's an idealized engine and it's not practical? What was the usefulness of it?
Efficiency there.
I'm sorry?
It had really good efficiency. Is that- Well, it defines the upper limit of the heat engine.
There you go. That's its use. Okay, and a Carnot engine. Okay, so all engines operate in cycles. Okay, and the cycle was 2 isotherms and 2 adiabatic curves. Okay, but this is not practical. Okay, so this is a idealized. It's a theoretical engine, and here is a practical engine. Okay, the Otto cycle is a practical engine. Okay, and here's the cycle it works on. Okay, so we'll go over these steps. Okay, so intake stroke, you just saw that the intake stroke is when air fuel mixture is taken into the piston. Okay, then what do you do once you take the intakes? When you take air fuel mixture, then you compress it. Why are you compressing it?
To make sure that all the fuel gets burned.
You're prepping it. It's when you compress it, it's getting warm, and it's just at its just. You're compressing it just below its ignition point. Okay. Now, the more you compress, the more likely it is that all of the fuel will burn. But one of the problems you run into is when you're compressing, if you try to compress too much, it might self-ignite. If it self-ignites, you're pushing and this heat is pushing you back, you're wasting energy. That is called knocking, which I don't know, you might have heard of in cars. Okay, so pre-ignition is a problem in gasoline engines. Diesel engines solve the problem like this. What they do is they just compress air. Air will not pre-ignite. Get the air nice and hot, and then you inject fuel, and it'll just explode. So that's how diesel engines solve that problem. Okay. So you'd like to compress the air fuel mixture as much as possible and get it as warm as possible. Yeah. So in gasoline engine, that's limited. Okay. Now you've ignited the air fuel mixture, you released heat, and then this hot air pushes the piston, and now is when the work is done. So now is when heat is being converted to work. Okay. Well, is all of the heat converted to work? No. That gas is, even after expanding, it's hot, and you're expelling the hot air, hot gases. That's where you're dumping it into the atmosphere. Okay. So for every $5 of heat released, how much did you throw away? 4. Okay. So that's what happened. Okay. So that's the Otto cycle. All right. The efficiency of the Otto cycle is 1 minus R to the power 1 minus gamma. Gamma is the specific heat ratio, and this is a complex gas. So gamma for this air gasoline mixture is about 1.4. Okay, so let me write this down. 1 minus R to the power of 0.4. That's what it works out to. 1 minus 1.4 is minus 0.4, which is that. Okay, what is R? So R is, so here you took in the air fuel mixture and then you compressed it. R was V2 divided by V1. Okay, or V1 divided by V2. What factor did you compress the gas by? Okay, R was V1 minus V2. Okay, now notice, see the efficiency, you would like this to be 1, meaning you want this to be 0. So if the compression ratio were infinite, this would be 0. But remember, if the compression ratio is too high, you'll pre-ignite the air-fuel mixture. That's the problem. Okay. All right, so the efficiency of the Otto cycle can be expressed at that. For example, if the compression ratio is too high, the fuel-air mixture will detonate before the compression is complete. And then you'll be wasting energy. Okay. Very high compression ratios also put stresses on the components of the heat engine. So the actually efficiency of an internal combustion engine is about 20%. Okay. Diesel engines do not compress a fuel-air mixture, but rather air only. So now they can have a higher compression ratio, okay, thus avoiding pre-detonation problems. And then the fuel is introduced only after the air has been compressed. And you don't need spark plugs either. Okay, so the hot air will ignite the diesel. Okay. All right, so this shows you the diesel cycle, and there's the efficiency, and alpha is V3 ratio, V3 over V2. So this is when you introduce diesel fuel into the cylinder, and the diesel burned, and the volume increased at constant pressure. Okay. All right, guys, so that ends the lecture portion. So